Our final section for this lecture is 11.7. And what we're going to do is start off with our square root friend from a moment ago. But this time the question is, what would the square root of negative 25 be? Well, if you think back to the definition I wrote a moment ago, the square root is asking for the positive number b that we can square and get negative 25 back. Well, in fact, there's no way to make that happen. So if you think about a positive real number and try to square it, something like 5, and square that, you're going to get 5 times 5, which is 25. That's a positive 25. So there is no way to have a positive real number b that we can square and get a negative 25 back. But I would still like to be able to do this problem. So in order to figure out what the square root of negative 25 is, I need to actually define a new number. And that new number is called the imaginary unit. Now, if it's a new number, I can't use digits that I already know, because I already know what 5 means. I already know what it means to have 7 of something. So I can't use any of those digits. So in order to introduce this new number, I actually have to use a letter. And that letter is going to be I. And I is defined to be the square root of negative 1. Now, by doing this definition, I can actually fix the problems that we have with the square root of negative 25. And we'll see that in a moment. Now, the other thing to note then about this imaginary unit is that if I is defined to be the square root of negative 1, that means then that if I take I and I square it, I would be squaring the left-hand side, so I'd have to square the right-hand side. I'd end up getting a negative 1 on the right-hand side. So there are different versions of different problems, and in some problems we're going to focus in on this idea that I is the square root of negative 1, but on other problems we're going to focus in on the idea that I squared is equal to negative 1. Well, now that we know that this number I exists, we can define something called complex numbers. And complex numbers are numbers that can be written in the form a plus bi, where a and b are real numbers. So now that we have this definition then, I'm going to go ahead and write down some examples of complex numbers. And the first couple of examples are pretty straightforward, and most people feel pretty comfortable with them. So if I write down 5 plus 3i, 5 plus 3i is a complex number because it's in this format. We have an a that's a real number plus a b that's a real number times I. So in this case, our a is 5 and our b is 3. So 5 plus 3i is a complex number. Now, sometimes if I change this up and now have 7 minus 9i, people look at that and say, oh, that doesn't follow the directions here. It isn't in the form a plus bi. Actually, it is. And what you have to realize is that the addition is just hidden a little bit. So if we think about this off to the side, we have 7 plus, and then what number could I add here to be equivalent to subtraction? Well, it's just a negative 9i. So 7 plus a negative 9i is the same as 7 minus 9i, and because of that, it does actually fit our definition. So 7 minus 9i is a perfectly acceptable complex number as well. Well, how about 2i? Well, 2i is also an example of a complex number. Now, it also happens to be an imaginary number because it doesn't happen to have a piece out in front. So we have an imaginary number, but it's also a complex number. So when you look at this complex number 2i, again, you might say, wait a minute, it doesn't satisfy this definition precisely. Well, again, it does, it just happens to be hidden a little bit. So I said that there is no number written out in front, but in fact, we can say a number that you can add to anybody and not change it is 0. So 2i can be thought of as 0 plus 2i, and everything's going just fine here. Well, the last one is one that a lot of people look at and say, hey, wait a minute. 4 is an example of a complex number as well. So how do I think about this one? Well, in this case, I have the part in front, but I don't happen to have something involving I. So it's 4 plus, how many of those I terms? 0 of them. So that's the game that you have to play on that one. So now that we know that, then, there's something important to note here. Every number that we've talked about previously in the semester is going to be a complex number. In particular, every real number is a complex number as well. And that's worth writing down. So let's write that off to the side. Every real number is a complex number. So in fact, every number we've talked about in the semester has been a complex number. We just haven't made a big deal about it. Now, you also have to be kind of careful about this definition. You can't go backwards. I can't say that every complex number is also real, because 5 plus 3i was complex, but 5 plus 3i is not real. So it goes one direction, but not the other. Every real number is complex, but every complex number is not real. So now that we have that information, then, the last thing that I want to talk about on this board is the fact that we can take these two numbers, a and b, and give them names. So this a is always going to be called the real part of the complex number, and the b is going to be called the imaginary part. Now, if you're not catching this, I want to make sure that you're seeing that I underlined the b, but not the I. So the b is called the imaginary part. So with that in mind, then, we can look at each one of these examples up here and talk about who is the real part and who is the imaginary part of each one of these numbers. So 5 plus 3i, the real part is 5, the imaginary part is the number 3. 7 minus 9i, the real part is 7, the imaginary part is the number -9. Real part of 0, imaginary part of 2, real part of 4, imaginary part of 0.